So welcome everyone. Palash is going to start very soon. I just wanted to take advantage of this free time that you have to talk something about the this particular class project. So look, the idea is this, that most of the time you see that there are a lot of research papers which actually deals that how can we develop a very good kind of system. So one example we have taken today, that if you want to develop a face invariant recognition system, so how you should go ahead with that. So it's a very important computer vision problem, and you can find out very relevant papers in this particular domain. So many papers are available. You just search on that, and however there is a limitation of the databases, so not much databases are available. I'm also not sure that how much this particular database is going to help you, but we have actually thought in this particular direction that if you are taking five movies of the same person with a 3-year duration, at least the distance would be 15 years from one image to another image. So at least this much we are going to ensure that 15-year distance, how can we develop a system that can recognize the person? So this this effort that we are going to do with this, we are going to have a database. But now after collecting this small portion of the even a small portion of data, you may be able to appreciate that how much effort the people are going to do in collecting the data. So, all right. So, with this idea, you are going to be a part of this particular process. And the process is this: please understand that you are collecting a part of data, and the complete database would be made available to you for your download and for your conduction of the experiment. So at the end, you can also target some of the conferences which are there and write your results in that particular conference. Even this particular database is a novel database that you can publish over there. So I call upon you that you must take it very seriously, and execute the things and get the result, and try to write the paper and submit somewhere.
Sorry, I was on mute. So, welcome everyone to this session on face recognition systems. Thank you all for coming on a Sunday morning. Wanted to give you a small heads up that this session is actually about. We'll talk about the basics of facial recognition and the kind of prerequisites and the ideas that you need to build a project like that. So we're not going to be coding a lot of things today. We're just going to be exploring and reading a few papers. We're going to be talking about what exactly is needed. Give me a second, please. Sorry. So we're going to be talking about like how to build a system in general, what data sets are available, what kind of processing is done, what kind of models can be developed, what kind of techniques do we need to solve the current setbacks or drawbacks of the present facial recognition systems. Before we do that, let's actually talk about what exactly is face recognition and how is it placed. So you see over here, this is a normal street in I'd say China, and you'd see that it's actually very common in China to have facial recognition systems implemented in streets. So, in fact, I've heard people say that they've, I think, by mistake missed a red light and walked on the what do you call the footpath, the walking the zebra crossing, and they immediately within 15 to 20 seconds got a message on their phone that this and this so and so fees has been deducted directly from your bank account. Now, how do you think this is possible? It's only possible because of facial detection systems that they've implemented. So they can directly go through, scan any faces or any people that is seen in whatever view, and run it through the systems, identify that this person is basically this. The money is directly, and then sort of detected from our bank systems. It might sound scary, and it is. And we're going to talk about some ethical implications as well. But facial recognition, so in the sense, as the name suggests, is simply recognizing faces in a particular computer vision scene, right? Now, it can be as simple as drawing a small bounding box across the faces, uh, and they can, in fact, you can have systems that do segmentation of particular faces, and there are algorithms to do that as well. But the idea is basically going through the entire scene and localizing that small box which has the highest likelihood of having a face in it. That is called facial recognition. Now, if you want a very basic example of facial recognition system, you'd see that I can give you an experiment. Most phones actually have a facial detection system. If you open your camera and if you were to sort of run it across your face, you'll see there's a small bounding box that's been created over there, a yellow box, if you can see, right? And that's a facial recognition model, although not extremely sophisticated as you might expect, like an extreme deep learning model, but it's a small algorithm. This algorithm is actually called the Viola-Jones algorithm. It's a very famous algorithm that came back in 2001 or 2002, I'd say. And it basically identifies certain features that are associated with a face, and we'll talk about all of those. So with all that, let's actually start with talking about face recognition, the history of face recognition, the current state of the art in face recognition. How do you, sir, please.
Just to add the Palash point, so face recognition has actually two parts. The first part where you actually going to detect that where the face is, it is called face detection. And Palash has rightly mentioned that Viola-Jones 2001 paper, very influential paper that actually solved this particular problem. That where is a face? This is the first part. So it is a different kind of problem. Look, you cannot combine the second part where after cutting his face, we are going to match and tell that what is the ID of that particular person. So that is the second part where we actually wanted to tell that what is identity, and this is the face recognition parts. Okay,
right. That is true. We'll talk about exactly how to develop all these models in this session.
so
And sir, please,
in your
please.
in your case, you have actually done the face detection part most of the time because it's not a crowd images. You have by yourself uh, cut those images and did a kind of as we have assigned that you are going to do a cropping also, huh? So after the cropping you are getting the face, so this detection part is already done for your scenario. Palas, please go ahead.
Right. So face recognition in essentiality is basically a method of identifying or identifying and then optionally, and in many systems, identifying verifying the identity of a particular individual using a given area where you think that there is a face. So it was actually one of the most famous computer vision algorithms back in the day, especially in the 90s and early 2000s. Very large commercial interest. So all camera companies, like if you guys remember the cameras that you got from Sony or other companies, they were all working on this technology. A lot of money that has gone into this. And recently, then there came deep learning, and deep learning, of course, took the entire scenario of facial recognition to the point where we are today. The basic idea behind face recognition is to sort of find a way to localize a particular face. So that's step number one, and we're going to talk about like different methods to do that. And second one, then doing whatever processing you need on that small local area to improve the prediction and to do any sort of further tasks like recognition of the person and so on. Let's talk about give you a small history behind face recognition to actually talk about like the basic algorithms that you can utilize.
Palas, can I speak for 1 minute?
Yes.
Okay, so one thing that I wanted to bring in front of you, that I have written these three words. Okay, can everybody see that, Mohit? I have
Yes,
written
sir.
identification, verification, and recognition. So these are actually the technical term. Okay. However, in a general discussion, you think that all these words are same, but they are not. Let me tell you their difference. So the difference is this, that identification and verification are the two things that actually we do. And recognition is something, if I say the recognize, it is a general word. Recognition means identification and verification both. Okay. If I say that I want to do the recognition, it is a general word. So generally we should talk about like that. I want to do face recognition. But if I say identification, it is a different thing. Verification, it is a different thing, totally different thing. Okay. Let me tell you what. So identification is something that you got an image of somebody, and you want to tell that who he is. So how can you tell that? I am telling about identification. You have to identify that who that particular person is. You got an image and now you want to tell that who this person is. So definitely you cannot tell until you have a database. So let's assume that you have a database of all the student in my campus. So you are going to match this new image that you got with all the things which are in your database. Definitely you are going to get some score, and the highest score one, you are going to tell that looks like that this particular image is this particular person. This is called the identification. It's a very compute intensive task, because if 1000 peoples are there in your database, you have to match with the 1000 peoples your new image, and therefore it takes time. Okay, understand identification? I think I have written wrong. Spelling is some problematic. I think you can correct it. Identification. Okay. And second thing is a verification. Verification is a process when somebody comes and somebody tells that, look, I am Mr. Palash. Let me allow me to enter to this system. So what I would take, I would bring the image, because 1000 people's data is there. So the Palash data is also there. I would bring the image of the Palash and take a fresh photograph of the Palash, and I would match. So verification is two images are there and I wanted to match them. If the score is going to be greater than the threshold, I can tell that, oh, okay, Palash, you are allowed because your image is matching with the image that I have stored in my database. You go ahead. Otherwise, I would say that, Palash, give me another image. Looks like that you are not the same person. So Palash would be into the big problem. Palash would say, okay, system is, this is a very bad system. So there are two different things. Okay, they have different perspective also. So identification, these are the two things: identification and verification. In the identification, you don't know about the person to whom you are actually matching. So you have to match with the complete database, find out the maximum score. In the verification, it is known that the first image is of Palash, second image is of Palash, and now I want to find out whether the similarity is greater than a particular value or not. Recognition is a general term. That means if I want to do the recognition, means I am going to do whatever, identification and verification. So just for your understanding, students. Okay, thank you very much. Thank you, Palash. Please go ahead. Very good session. Yeah.
So as sir rightly said, the entire process of recognizing and sort of identifying a particular person is actually a multi-stage process, I'd say, and and different tasks are there, and there are different definitions of each task. So we talked about identification, and then said about verification. So talked about recognition. There's a small component that you may need, like the one I'm showing over here, which is called localization as well, which is not an extremely different task as well. But the essential problem now that we have is hand is that how do we define the problem? And how do we then create an efficient system to sort of build good solutions, good results as such. So I'll talk about now the reason I'm actually you might say that these are actually different tasks. Right now I'm not necessarily predicting which person is which, but I'm sort of creating local bounding boxes. But the underlying algorithm is essentially the same across all these tasks. You'll see. The reason being that they're all computer vision. You might have seen, like, even in almost all problems, they have a neural network in which the image is fed. The essential difference comes in the part where you define the problem itself. Like the problem in many cases, like classification, is to reduce the loss, a certain type of loss. In prediction, bounding box prediction, it's the reduction of error of a particular kind of loss. So that's the definition of the problem that changes, and the model itself, but the underlying algorithm and the underlying structures remain the same. So we'll discuss about a few things. There is, for example, back in the 90s when this problem was very new, people used many approaches like this that I'll show over here. It was called the eigenface approach, right? Eigenface algorithm for facial recognition. And basically, the way it used to work is that it used to take in a photo, it used to extract the most important features from it using eigenvectors. So that is essentially the PCA algorithm that you might have heard of, principal component analysis. And guys, I encourage you to sort of write all of this stuff, because it may or may not help you in the assignment finally in this. But it will definitely help you understand the problem better and to approach the problem better. So you have let's say a 28 by 28, so that's 764 pixels in total. And you would say that, well, I have a small classifier that can take in, let's say, 5 parameters at once. So I would choose the 5 most important features, and I would use to predict which person is which, right? So essentially, it does boil down to a classifier model. Now, it may or may not be like a neural network based approach that we talked about, because there were so many different methods, including linear regression or logistic regression or SVMs, different statistical based classifiers. So here what we're talking about is basically like what exactly do we feed into the model. That has been the major problem for a long time. Because right now when we see computer vision problem, it seems very intuitive that we would probably feed the image through, let's say, a convolution neural network, but that itself is like a very advanced technology. It's not very obvious why convolution should be applied over images, right? That's that. Then there was, so this class of models, like the one including this eigenface approach, is actually, it comes under the holistic model approach. And basically, that almost always dominated the facial recognition community as such. So what they do is that holistic approaches, they derive certain low dimensional representations. So in the sense, out of 764 pixels, they derive, let's say, 10 pixels, right? And the 10 pixels would then be put into certain kind of models like Bayesian models, statistical models, and there are a plethora of papers that you'll find on this topic. So that's the task. That's one of the tasks that you actually can apply. One of the methods that you can apply over your data sets, right, for facial recognition. If you guys find it hard to visualize, I'll probably give you a good example that you can keep in mind whenever you want to visualize something. Is that, imagine a facial recognition system of an office in which you have to show your face in order to get your attendance registered for the day, right? You would go over there. The model would take in your photo and it would match it against the database. That, are you one of the people within this system? And the model would either accept you or reject you, right, based on how efficiently it runs. And now you realize that it's not a simple one-to-one matching, in the sense it's not like just that the part where is this person the same as like one of the photos that we have in the database. Well, you might be wearing a different t-shirt, you might have certain facial beards, you might have I don't know, different haircuts, you might have different like background lightings and so on and so forth. And the task of the model essentially is to identify features that help correlate between your face and something else, a base reference, like a photo that I might have uploaded to the database. So that's the facial recognition system that we're talking about over here. So the very first approach, I'm going to create a document. Give me a second, and I'll put in all my points. Right. And I'll share this document later on, but let me just start writing. So this is known as face recognition. I'll keep this session very short. We'll end it by 11 maybe. So imagine the simple task, the attendance registering system for an office that uses facial recognition, right? You would show your face to the camera, and it would run it against the database that is available. So even though you might be wearing a different t-shirt, or there might be dimmer lighting, you might have a different haircut. The model's task is to identify features that are unique to you, right? Unique to you, and that is the task of face recognition. So, for example, something unique to just you, maybe well, you may have a particular color of eyes. The distance between your eyes may be unique, right? The length of your forehead. Maybe. Forehead is also a good indicator, right? All right. Some algorithms that we are going to talk about, this is also going to talk about the history of face recognition models. So early 90s, there were something known as holistic, or holistic approaches. So for example, you had eigen-face method for face detection, in which you do PCA to identify a lower dimensional representation of a face, feed it to the model. So this is gonna give you so holistic models are basically derive important features and feed to the model, right? And this was the major approach back in the 90s, I'd say. Then comes early 2000, in which there were local feature-based methods, right? You have early 2000s, in which you have local feature-based methods. This included handcrafting features from images to derive good amount of information from a person's face, right? So if you guys looked at the assignment, the PDF file that they showed, you'll see that there are certain algorithms, like Sir has mentioned SIFT, or he has mentioned ArcFace, pause face, right? I'll talk about something known as like Gabber filters, maybe, right? local binary patterns. We'll see over here. The basic idea was basically process the image in such a way that you get certain features which will help you identify a face. So let's talk about SIFT, for example, SIFT face recognition. What exactly we're doing over here is that, yeah, that's a good explanation of the different types of methods that we have. So let's actually go to the SIFT paper that I was seeing just now. Okay. All right. So the essential idea is to identify regions in the area which will give you high activations as such, which are much likely to contain important information that can help you identify a person specifically. There's different functions that have been defined over here, but essentially that's so the idea is to find local features, right? Similarly, there's orb, cos phase. We'll talk about Gabber filters, for example. Gabber filters for face recognition. You'll see that there's actually a paper on this. So I'll put a link to that. All right, so basically what we're doing is that they extract Gabber. So let's talk about like what exactly Gabber filters will look like, and I'll show you. Can't find a visualization. Right. So Gabber. So do you guys find this picture any familiar? The one that we've seen before. So it's actually very similar to a convolutional kernel that we talked about, except that we've looked at kernels that are automatically learnable. Gabber filters are basically convolutional kernel type approaches in which you hard code certain features, and this will allow you to identify, let's say, for example, uh, certain characteristics of a face in general. So, for example, when we talk about the Viola-Jones algorithm, the way Viola-Jones works is that it will look at certain. Yeah. So what it's going to do is that there are certain features about a face that you might say that is common to all sorts of faces. Let's say, for example, there is you might always see, almost always, that the eyes, the kind of cavity of the eyes is sort of darker than the forehead and the part below it, which is the nose part. And so a filter which says that any area where there is a white, black and white, and you can build a convolutional kernel for that, is supposed to be the region of the face where there are eyes, right? And then another feature is that the nose is the one over here. You see the nose is lighter in color than the things on the side of it. So these are methods that were actually used, and these are features, right? uh, Essentially, whatever problem you have, this is not just about general face recognition, but even not just face localization, but also recognition, in the sense that whatever data set you feed your model, you're going to teach your model how to look for certain features that are specific to the examples that you've given in the data set. So for example, if any one of you collected images of Amitabh Bachchan, for example, Amitabh Bachchan face will have certain features which will fit certain filters better. And so you're teaching a model to sort of differentiate different images based on that particular filter. So that is the idea behind facial recognition, right? Then you have right? Early 2000, let's say, early 2010s, right? There was something known as learning based local descriptors, right? And basically you're adding an element of learnability, through a neural network model or a linear regression model. Define a problem and you'll be applying your algorithm to that anyways after that. All right, enough of this. How do you actually build all these models? So we'll actually look at different algorithms that different methods in which you can build actually the code for this. I'm going to go to this library called OpenCV, which contains certain methods to do facial recognition. So there's this method called HAR cascades, classifier training. Cascades are nothing but like basically different filters that are stacked on top of each other, right? So which work parallelly. So there might be certain methods to detect edges, certain features to detect lines, and then different methods like the detection of the areas of the eyes and other things like that. So I'm going to take a small, right, let this be 3. Right. Anyways, methods to build your face recognition system. All right. Actually put this algorithm, this link over here, and let's talk about like what's going on over here. Look at this. This is just face localization. I said face detection, not identification or recognition as such, in which you have taught your model to give the most what do you call activations to the region where this face is contained, right? And that is given by those small images that you've captured through in your data set, right? Because when you feed it through your data set, your model is actually learning to give high activation to any subspace of the entire scene where the kind of features exist. So similarly, you can just not recognize the face, you can recognize the eyes as well, right? And now what I can do is I can on the same model, what I can do is create 2 subtasks in the says, and then I say, and I build a classification model out of it, and I say one image is that of Shah Rukh Khan and one image is that of Amitabh Bachchan. Your model would then learn to identify features that differentiate them both. So for example, it will learn to calculate that when certain edge features are computed, certain types of values you get for Amitabh Bachchan and certain types of values you get for Shah Rukh Khan. And that is how you would do your facial recognition system, right? Then I would probably so that's the basic idea behind that. Let me open this paper over here. It's basically which basically talks about all sorts of algorithms that have been used in the older days to extract features and to build your models. So let me not go through uh, the the algorithms such, but here's one such method. For example, pass it through a filter like the Gaussian skin model, in which you'll get only regions where there is skin, most likely, or something similar to that. On that, you would run certain algorithms. So for example, over here, they're trying to reduce the number of features. So for example, they removed all these facial features, and you get basically the outlines of the face itself, and you get the detection of the face itself. But now let's say on top of that, I will build a model in which help learns to identify between these two people. I can build that, and that becomes a facial recognition system. But the underlying fundamental structure will remain the same if you guys see as such. So you see that this model works in this particular way. So you're giving it certain faces over here, and you're teaching your model to give higher values to certain types of features. That's it. All right. Now, with parameterization, you can teach your model anything you need. You can not only teach it finding a face, but also recognizing it, and that is the model building part, essentially. All right. So here is early 2010s. Now let's come back to mid 2010s. So Facebook comes with deep face and face deep ID. So Facebook deep face. Go to the original paper. Yep, deep face. I'll put the link over here as well. Is that so? Let's download the paper and see for ourselves. Essentially, they introduce what we know today, which is using convolutions or convolutional neural networks to identify faces in particular. And convolutions are basically learnable filters that you can use to adapt to whatever situation. So they might have given the goal to the neural network to identify a particular face, and the model comes up with this. And the model can essentially identify it. And once the community showed that convolution or convolution neural networks can be used, there was no going back, right? That's that. No. Right. Then there's deep ID and other things like that. So there's that. And they actually showed on this data set's called labeled faces in the wild data set. So I'm going to create another section over here that talks about data sets specifically. For face recognition, you have labeled faces in the wild. So LFW dataset, right? Which you can use to have different faces with different labels, and then you can build your model accordingly. And so give me a second, guys. Sorry, guys. So this marks the beginning of CNNs for face recognition. Right. We'll talk about all these data sets, but I can give you a list of all the sort of a list of all the data sets that are available for this task. So sorry. There's celebrities and frontal pose in the wild, cross pose, LFW, so different poses altogether. So you can make a model invariant to the position of your face as well, like the way if you're facing to the left or to the right. Just to give you an example, if you were to look at the bounding box algorithm that is implemented in your camera phone, you would notice that if you were to turn your face to the side, the box disappears. And if you have someone in your acquaintance who is of a darker complexion, the model does not work very well again. That is simply because of the complexity of the model. It's a very simple model. The more complex and the more sophisticated you can make a model, the more invariant you can make to all these issues over here. All right, so here's a basic here's a basic model building technique for face recognition. So you've already fed the model. You've already fed a data set of faces that you want the model to identify. So, for example, I'm going to take a few actors. Not Amitabh Bachchan. I mean, I'm bored of it. Well, Hugh Jackman. Daniel Craig, and maybe name some actor/actress. Okay, let's take. All right. And you build a model that identifies features of these people. So, e.g., a deep learning model. So, a very basic that I would basically do is deep learning image classifier model, right? Take a photo. So, using cross entropy loss, right? That's that. So that's the face recognition model. And you might say that okay, and so now you would say that if you can build sophisticated models like deep learning models, what issue do we have over here, and why are we even talking about age invariant factors over here, right? What issue do we have? Isn't the problem solved? Such. Turned out no. Right. So it turns out that there are way too many types of features and variations within features. So different people have different types of jawlines, face structures, and so on and so on. And so you can either build infinitely complex deep learning models and struggle to make it learn all these subtle features, or you can build simpler models, which sometimes you do have to do a trade-off, and then you have to identify a method to mitigate these problems. So consider age variation. Uh, uh, so it was a very common problem uh, to have to for the model failing to recognize the same person at different ages. So the data set, for example, had only images of a young Hugh Jackman, right? Now, when you ran the model uh, for the for the present Hugh Jackman, the model failed because initially it learned the wrong features, and now you're actually paying for it. And there is not a lot of ways to identify like what exactly the model is learning, because it's essentially a black box approach, right? Especially when you talk about deep learning, or when you talk about parametric learning and PCA and whatnot. So problem over here is age invariant face recognition. Uh, and what is the problem? What is the problem statement? That your model learns features that are robust to age, to the aging factor. And there are different variations to this. I mean, what about different lighting scenarios? There are algorithms that are there are papers specifically based on that, learns to aging features. Uh, right now, you guys are building a huge data set, right, containing different features, or different variations in the aging process. You're all choosing different people at different ages, and you're going to train your model to learn features that are independent of features, right? So that's the most basic approach. The most basic approach to the age invariant model is basically augment the data set to contain these variations, right? Because when your data set is going to be larger, in that way your model is going to learn is going to be penalized when it learns the wrong features, because if it learns the wrong features, it won't be able to get a good accuracy on people on different ages. And so you're going to be working with that basically, right? So we're going to talk about a few methods that have been used to augment this data set. It's not as simple as simply just building this data set. And so maybe just a good idea, when you get this what do you call this the assignment on this, what you can do is you can think on these lines and develop methods if you want to. So let's talk about a few data sets that already exist on this. So we talk about, for example, very similar to this. I mean, you're building a custom data set, but data sets similar to the data set you are building. So there's the celebrities aging data set. It's called CACD, if I'm not wrong. Right. So cross age celebrity dataset. So different celebrities at different ages, similar to yours, but I don't think it's as large as you would have. There's the morph dataset. So morph dataset. And it's a basically it has ground truth labels of people at different ages, so you can make your model learn on that as well. All right, so that's the first method is this way you can augment your data set to contain age variation, and make your model robust on it, right? How do you further augment this data set? Because here's the problem, right? I mean, you guys were facing the problem of creating a large data set, so you asked Sir to reduce the number of images. So now we're working with 25 images only. But then what if 25 images are simply not enough to capture the age variation, right, of the people? So some modern methods include Gans, which you create synthetic faces by interpolating different ages. So for example, I might have pictures from the age 25 and then may have pictures from the 40. Gans can actually create ages, create faces of those ages through, their own tasks through a variety, through their algorithms, and you can have like a much larger data set, for example, over here. So here's an example. Look at the same person over here at age 23 on this number 23, and you'll see that slowly they have been able to build a model that creates images of different ages over here. So for example, let me take a screenshot of this. I'll put it over there. For example, put the link to this paper over here as well. Start. Right. Yeah, that's one method you can actually do that, right? And if you guys know about the Face app that you can download on your phone, it uses Gans to produce an older version, right? Older version of yourself. Face app old. Right. You must have seen these sort of things, and these are actually very robust. So these are methods to overcome that. All right, that's that. So much so for face end of face face recognition. Right now, so we've talked about face localization. Not a very different problem. Use build a YOLO-like model, like for bounding boxes that uses non-max suppressions to identify areas of the image that most likely have a face. All right, that's just an example, by the way. All right. we've talked about face identification, build an image classification method, can apply the classification only on the bounding boxes. So that's an advanced version of the traditional image classification, right? All right, let's talk about face. Oh, let's see what Sir also mentioned over here. All right, so that's identification and recognition. They're both basically the same things. But let's talk about verification now. All right. And then how can you how do you verify that the person is the same as you've recognized? So let's talk about the Siamese network problem for that. And essentially, imagine this office attendance system that has a database of your photos, one or two per person. And so you might know that this amount of information is simply not enough, right? How then do you recognize me in different t-shirts, beards, haircuts, makeup, what do you call lightings, right? With just the small amount of references, amount of references. So that is essentially how Siamese networks. That is basically the problem that Siamese network introduced and solved. Siamese network. And so I'm going to copy this image. I'll put it over here. And so you would see that what I'm essentially trying to do is, again, basic modeling remains the same. Only difference is the change in objective. So what I'm trying to do over here is I'm not trying to identify which image is a 0, which image is a 1. I'm simply trying to find similar features between two images. So here we are not extracting features from the class 0, but we are sort of creating a binary classification problem that tells whether or not the two images are of the same category. Now when you are going to build Jet versus imposter graphs, which is going to come in the next phase of this problem, you are essentially using certain features to match two images, right? Now, pause face, arc face, shift are simple features, Siamese network basically the sophisticated version of this. All right, that's basically, this is face verification. I've actually built a lab on this. Advanced computer vision continued. I've created a lab on this, which you can see, in which I've talked about like the Siamese net, how to build Siamese networks in PyTorch and some libraries. And so you'll see that, and so what you can do essentially is that you have now made your model more robust by it giving it the ability to identify two images that are sparse in number, in the sense the data set itself is very small, but you've still identified it. And now it obviously goes without saying, larger the network, the more better your model will be at verifying which two people are the same. So that's the facial identification system. So you see, slowly you're building an entire pipeline as such. So let's talk about what essentially you're going to be doing with the data. So your the assignment, and you're going to have a large data set containing celebrities at different ages. And build an age face recognition system. You can feed the entire data set to a model. It will learn features that are independent of age, right? And I can sort of that's that. Further augmentation using the techniques that we talked about, right? We can talk about, let's see what exactly. All right, now when you run your feature action, so okay, not very vague. Build model that derive features, arbitrary features, models. I can actually show you a paper talked about age and face recognition. Can't find the paper. Yep, this one. It's a paper from 2020 itself. Let me put the link over here. You see that, let's go to the model and see like what exactly they've done over here. All right. So it extends from an autoencoder based GAN to includes disentangled representation learning subnets. So it learns certain features, arbitrary features of the model using GANs. And the way you can build your GAN is simply basically in your GAN, your we guys will learn about GANs in the next lab session, which will probably be in the final after the midterms, basically. But basically, in your GAN, there's um, there's a generator. Right? It will produce. Let's different methods which can either produce either labels or images at different ages. Input will be older self, output is older self, for example. And the discriminator determines whether this output is real or fake generated, that is. And method, something like a component, and it will learn where is it? This method teaches the GAN to identify features important age for supervised learning, by the way, not self-supervised learning. Then we have what else do we have? There's a cross entropy and label smoothing, and basically that's basically the idea behind it, right? I mean, you're building identify features that are different. Now, an example, but it may not be necessarily the way they've modeled their GANs. So we'll talk about like basically that. Yeah, that is exactly what they've done. Exactly what they've done. So the model, you're teaching a GAN to take in a young face as the input and give an older person as the output. And then based on certain faces, the ability to sort of transition as such. That's it. And so the facial recognition, the idea behind face recognition, the kind of steps that need to be taken, and the ideas and the things that you can use to build your face recognition systems. Before that, okay, I think I'll stop as of now. This is basically the idea that I wanted to give you. Not a lot of no coding as such. I didn't code this particular lab session. But what we learned in basically is this: what exactly is the problem and how do we actually deal with it? When you're going to be building your models, it's going to be there is not just one solution to it, right? I mean, it's basically you give your model certain inputs, you train your model, you get certain outputs. And so basically what will change is how you define that problem. And that is basically what we've discussed in this particular session. So hope you guys found this small session intuitive, like very insightful, and hopefully you can take away something from it and utilize it in your projects. So thank you guys. I'll share this notebook or this document with Sir, and I'll put it on the website. All right. If you guys have any question, I'll be here.
So we can choose any of these approaches, right, for our exact.
I'm not exactly sure. Sir might decide as to like what method you will use and what you can use or what not use. I'm just giving you an idea that these are all the approaches that can be used. Just for a
Yes. Okay.
I mean, because it depends on. I mean, if someone is not really comfortable with advanced methods, then we probably have to reduce the complexity of the problem. But
Okay.